This is segment 7 of the module 7 lecture. And here we're going to talk about the confidence interval estimate of the population mean. And this covers sections 8.2, but primarily 8.3. All right, so in this segment, we're going to learn how to use the sample mean and the sample standard deviation to construct a confidence interval for the population mean. Now, I wanted to note one thing is that if the population mean is not known, that also means that the population standard deviation is not known. Because the only way that we know the population standard deviation is if all the observations from the population are known. That implies then that the population mean must be known. And if you remember in module 3, we saw the equation to calculate the population standard deviation. And that equation uses the population mean. So what we discussed in the previous segment, where we were assuming that sigma was known and we were constructing the confidence interval for the population mean with sigma in the equation, well, that didn't make a whole lot of sense, because if you knew sigma, you must have known mu. So why compute the confidence interval? So in here, instead of doing that, we're going to focus on using what we know. That is the information from the sample mean and the sample standard deviation. So in your text, you're going to find a diagram like this. And in section 8.2, the book shows you how to calculate a confidence interval when the population standard deviation is known. And they use the standard normal distribution in that section. So again, I'm not going to focus on that aspect, because we know that if the population standard deviation is known, the mean was known. So it doesn't make sense. However, from that section 8.2, we're using the equation to calculate the minimum sample size. All right, what I'm going to focus then is on using the confidence intervals that are presented in section 8.3, where the population standard deviation is not known. And the confidence interval is calculated using the sample statistics, the sample mean and the sample standard deviation. And we're going to focus on two cases, and that is the cases where the sampling distribution of the mean is normal. That is when the population is normal, or the population is either unknown or not normal, but the sample size is at least 30. In both of those cases, the sampling distribution is normal. And you will see that because we replace the population standard deviation with a sample standard deviation, then we'll use this t distribution. Also, this case 3, where the sample size small and the sampling distribution is not normal, then we use a method that's beyond the scope of the course. So we're not going to discuss that case 3. So we're going to look at this case 1 and case 2. All right. The t distribution, we said that that distribution can be used when the population standard deviation is not known, and we replace it with the sample standard deviation. And also when the sampling distribution is normal, either because the population distribution is normal or because the sample size is 30 or larger. If that is the case, then the t statistic defined as this follows a t distribution with n-1 degrees of freedom, or df. And I put this, the definition of the z-score for the sampling distribution of the mean that we saw earlier, and you see that this equation is the same equation as this, with the exception that for the t statistic we use the sample standard deviation, and for the z-score we use the population standard deviation. So we're going to use this statistic with the t distribution. All right, the t distribution is similar to the standard normal distribution, and that is bell-shaped and symmetric, and that the total area on the curve is 1, and that the mean of the t distribution is 0. But beyond that, there are very important differences between the t and the standard normal distribution. One very important one is that the t distribution is defined by a single parameter called the degrees of freedom, which is the sample size minus 1. Now, this tells us that there is not only one t distribution, there are many t distributions, one for each sample size. So we're dealing with many t distributions. Also, the standard deviation of the t distribution is always larger than 1 and is defined by this equation here. And only when the sample size is very large, then the t distribution becomes the normal distribution. So the key characteristics of the t distribution that we're going to rely on is that it's symmetric about the mean of 0, and that the area under the curve is 1, and that is defined by the degrees of freedom, or the sample size minus 1. All right, so we're going to use a table, table 5, to find t-values and find probabilities. One big difference between table 5 and table 4, which is the one for the standard normal, is that table 5 shows you a different t distribution on each row. And because each row is for one particular t distribution, for the degrees of freedom of one particular t distribution, only 6 probabilities are given. And those probabilities are to the right of the t-value listed in the table. These t-values, these probabilities are to the right of the t-values listed here. So remember, in the standard normal, the table 4, the probabilities were to the left of the z-value. This table gives you the probabilities to the right of the t-value, and each row represents a different t distribution. Let's look at an example to see how we use table 5. So in here we want to find the probability that some t-values of 0, the values of the random variable t are bigger than some value t sub 0 with a probability of 0.05. And so we're dealing with a t distribution with 16 degrees of freedom. So we're going to find the t value in table 5, and we're going to use the probability on the right tail as is shown right here. All right, so now the way we use table 5, the first thing is to find the probability you're looking for, and here is 0.05. And then you go down that column until you find the degrees of freedom of the t distribution that you're looking at. And then when you at the intersection of the column and the row, you will find the t-value we're looking for. So here the t-value is 1.746 for a probability that t-values are larger than this t-value of 1.746 with a probability of 0.05. All right, sometimes we're going to need to find the probability on the left side of the distribution, or to the left of the t-value. To find that, we're going to rely on the symmetry of the t distribution. And so we're going to find the t-value for the same probability we're interested in, but on the right side. So once we find the t-value for that probability on the right, and because we're looking for the same probability on the left, so the t-value on the lower end is just going to be the negative value of the t-value we found on the right-hand side. So that's how we find probabilities on the left side. For a given probability, we rely on the symmetry of the t distribution. All right, so now that we saw how we use table 5 to find probabilities from the t distribution, or from the multiple t distributions, the next question is, well, then how do I define the confidence interval in terms of the t distribution? Well, we do it exactly in the same way that we did for the standard normal distribution. So we rely on the level of confidence to find the probability in the upper and lower tail, just as we did with the standard normal case. So in here, the confidence level of 1 minus alpha is for this interval symmetric about the mean. So the alpha probability that it remains outside that interval, well, we split it between the two halves in half. half on the lower tail, half in the upper tail. So this alpha over 2 value, together with table 5 and the degrees of freedom, or whichever t distribution we're working with, will give us the upper t value. And you know that by symmetry is the same value on the lower end. So now with that information, we use the same formula that we derived for the standard normal. We use that to calculate the lower and upper limit of the confidence interval, but now in terms of the t distribution and in terms of the sample standard deviation, the sample mean, and the number of observations in the sample. So all this information is known. We're not making any assumptions. They are derived from the sample, and the t-value is derived from the confidence level that we are interested in. All right, so with that, then the book expresses that confidence interval like this, but I'm going to be working with these two equations because those are the equations that we use to find the upper and the lower, the lower and upper limit of the confidence interval explicitly. So I will use those two equations. Another thing I wanted to point it out to you is that this part of the confidence interval is now the definition of the margin of error in terms of the t distribution. So it's the t value for alpha divided by 2 times the sample standard deviation and divided by the square root of the sample size. So that's how the margin of error is defined now. All right, and let me stop here. So in the next section, we'll discuss 2 examples where we apply the confidence interval for the population mean using the sample statistics and the t distribution.